So we talked a little bit about the global ocean current last week. I'm not going to rehash that too much at this point in time. Just remember that the Pliocene, well, okay, maybe it is important to just to help reset the stage. That what was it that led to the global ocean currents getting rerouted and changing direction, changing the course of the cold currents? We talked about a couple of examples, but which one in particular was really monumental in helping to develop ice in the North Pole? Ken?
South America disconnected.
That South America disconnect was real important. That's right. Now, keep in mind, though, that one happened a fairly long time ago. I mean, we're talking about probably, 30 million years ago, that, or at least 20 million years ago, that disconnect happened to where polar ice began to develop in Antarctica. And then we talked about that positive feedback loop, where as more and more ice builds up in Antarctica, it's cooling the global temperature down. Eventually, though, ice will develop at the North Pole. And what will really help that ice, the ice sheet at the North Pole, particularly over Greenland, what really will help that grow? It's another change in the global ocean currents. Kiki? Yeah, the connection with North and South America. Now, we'll talk about that today. There's a little bit of scientific debate about the timing of that, and I'll introduce that in a bit. But generally speaking, for over 100 years, it's been fairly established as rigorous scientific sort of the nearest thing you can have to a scientific fact, that North America and South America were connected by a land bridge probably around 3.5 million years ago. Some of the science is debates about when that timing happened. But what is clear from the scientific record is that land bridge connection established, thereby cutting off the ocean currents, leading to the development of more ice over the North Pole, over Greenland. So yeah, it's been a massive factor. Do we know all of the mechanisms by which it happened? Not entirely, but we know many of them. So this is an artist rendering showing what North America looked like at the as of the early Pliocene, or actually sort of the late Pliocene, 3 million years ago. You can see there's a buildup of ice, an ice shelf over Greenland here. And some of the major events of the Pliocene include the dramatic rise in sea level. Seas were then about 35 meters higher than they are today. So take a look at, let's say, most of Florida, for example. Look how high the sea level is. Parts of central Florida around Orlando, the area just north of Lake Okeechobee, kind of exist as this upland peninsula, right? But a lot of South Florida and both coasts of Florida are underwater. Look at also like South Alabama. Most of Alabama at this point is above, but just the very bare coastline along the Gulf Coast is underwater because of those high sea levels. As of the Pliocene, we see the reopening of the Bering Strait. So that water body that formerly disconnects the land bridge that is Beringia. Remember, that land bridge had been connected at various points. It has been connected and disconnected. So at this point, going into the Pliocene with these higher sea levels, we would expect that land bridge to be covered up or drowned. And that's what we see here. So that's going to restrict the movement of species back and forth. Keep in mind, we don't have people migrating at this point because humans as a species have yet to evolve still. We have the uplifts of the Rocky Mountains, the Sierra Nevada mountains, and the Coast Range mountains out on the West Coast. Still, all of that is beginning to change the climate and the landscape out in the West. And with the growth of those glaciers up in the Arctic, that means things are continually cooling down. So tropical vegetation is continually sort of disappearing from North America. We had a lot of things here from the tropics. That's sort of beginning to wane or disappear entirely. And then finally, toward the latter part of the Pliocene is when we have this land bridge connection that forms with Central America. We talked about that. No need to kind of go back over that. I have added a couple of images here to the PowerPoint. These have all been uploaded now, this new version. You can see a lot of those mountains there is all volcanic mountains. The lowlands would be of recent origin. So they would be areas where the igneous rock has formed more recently, establishing this land bridge connection, allowing plants and animals to move freely across. There's an article here that is, I think, hosted by MIT, and it's a great article that also speculates on some of the disagreements that are in place among the scientific community on when this timing happened. Again, for over a century, people have thought it's been around 3.5 million years is when that land bridge formed. There's some new emerging evidence. It's not entirely clear from the article. However, that suggests maybe it was 10 million years ago or 15 million years ago that land bridge connection began to happen. So I just encourage you to read that and find out more for yourself if you're curious about that topic. We talked about how the climate was warmer in the Pliocene than it is today, but it was cooler than it was in the Miocene. But still, it was warm enough to where we had things like alligators, for example, at about the same latitude here in parts of Tennessee. I'm going to emphasize some of the animals that we had in a minute, and you'll kind of get a feel for what the climate must have been like based on the animals that were present. So we've already reviewed a lot of this, but I would urge you to go back and make sure you kind of study up on what the climate of the Pliocene was like. In terms of the changing forests and grasslands, all the ecosystems, remember that's what we're going to talk about in the whole latter half of this class is doing a deep dive on different ecosystem types. So right now, I'm just trying to sort of introduce some of these types of concepts to you. Let's take a look at some of the prevailing things that are happening during the Pliocene as far as ecosystems are concerned. The Southern Appalachians during the Pliocene would have had many of the same modern elements, as we call them, same type of plant groups. Hemlock trees and oak trees and pine trees, maples and hickories. They were all, many of the same groups that are present today were present then. But you had a high number of East Asian species. And that's largely a holdover from like the Eocene and the Miocene. Many of those species that had been swapped across those North Atlantic and North Pacific land bridges are on their way to disappearing completely from North America, becoming extinct. You also have a lot of taxa that are today more traditionally found in the Deep South, places like Florida or Southern Texas. And there's even a few things here that indicate that we had some Western desert species in this region, like Gila monsters. And there's a shrub called ephedra. You know, you may have heard of the medicine ephedrine, which comes from a southwestern desert shrub called ephedra. We have evidence that ephedra was growing in East Tennessee during the Pliocene. So we have some southwestern things as well. Okay, let's tell you a quick story now. Let's talk about a site called the Gray Fossil Site. This is a site that came to be known probably in the late 1990s. The Tennessee Department of Transportation up in Johnson City, Tennessee, which is where East Tennessee State University is located. TDOT was in the process of trying to fix a intersection where there was like a T intersection. It was a very dangerous place where there had been some recent fatalities. And so the Department of Transportation wanted to redesign that intersection, and it required bringing in bulldozers and like bulldozing a new intersection that was less dangerous, where you had better visibility and line of sight. So they called out the bulldozers and they start, you know, doing the things that they do to try to make a new road and improve this highway. And the guy's on the dozer and he's up there, crank, 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 and you know, there's buzzers going off and beeping sounds, and backup noises and all this stuff, right? As they begin to dig into this earth that is the side of this hill, they all of a sudden realize that they're digging into the purest, grayest clay you can imagine. Okay, I'm talking about the most solid dark gray clay possible. Is there even a color in this room that would like symbolize how pure and gray this clay was? Help me out. Like maybe the back of this Dell computer. Just a really, I mean, we've talked about soils, right? We've covered alpha soils and mollisols and ultisols. We never talked about something being a dark gray clay. So to geologists who are on the Department of Transportation staff, well, first of all, when they hit this gray layer, even the operator on the bulldozer was like, hey, Jimmy, we hit something weird. And then Jimmy comes over and he looks at the side. He's like, boy, look at that. That's the richest, purest clay I've ever seen in my life. They did just a little bit of digging with their hands and kind of probing, you know, they kind of put their finger in the clay. And it was like pure clay, like potter's clay, pure. And they're kind of, wow, that's some pure clay right there, boy. I tell you. And then all of a sudden, as they were just kind of, you know, putting their finger in there, this bone fell out. And they're like, uh-oh, we got ourselves there's some kind of a dead human or animal here or whatever. So they called their supervisor and they said, hey, Chief, listen, we got out here on the site. We got ourselves some pure clay, well, you know, like we've talked about a few years ago. Yeah, we got bones coming out of here. Yeah, you better send the geologist down here. That's right. Okay, we'll wait for you. Don't worry. We won't do nothing. Yes, sir. Yes, sir. Thank you. So they wait and the geologist comes out, right? He's probing around and he's got his rock hammer, you know, and he's looking at it. Guys, I think right here what we have is we have some ice age collections. Okay, I'm looking at this bone right here. That looks like it's definitely from the Pleistocene. You know, this is probably just falling on, you know, Pleistocene probably didn't mean much to a lot of people out here working on this road, you know. And all of a sudden they start looking at these bones, and the first full bone that they actually get out of this mud and they kind of get the clay off of it. What do you think it is? It's the skull of something. What is it? It's not even a rhino. I think the first one, that was like second. So rhino was like right up there with the top 2 or 3 discoveries. I think the first one was an alligator skull. Can you imagine if you found an alligator skull? You wouldn't have to be a paleontologist or a mammologist or a herpetologist to recognize the skull of an alligator, right? So sure enough, they're like, wait a minute, hang on, we got an alligator skull over here. Now, how in the hell would that have gotten here from the Ice Age? That doesn't even seem like it makes sense, right? Ice Age is supposed to be colder, not warmer. So they continue to just shut the site down. All right, we're going to call it quits. No more work today. Go home. Might be next week sometime, Jimmy. I don't know. Just plan on coming back next week. Okay. Unless if you don't call me, I'll call you. Okay. Next week comes, no work. The following week comes, no work. They're shutting this place down because the more they dig, now the locals are looking over from across the fence. What's going on over there? My former grad student, his family lived on the highway, and he told me, he said, yeah, we just go over there and start digging out turtle shells and all kinds of stuff out of the side of this hill, right? The public was beginning to find and go in and dig at night and did their own fossil discoveries. Well, to make a long story short, the paleontologists were called in, the geologists were called in, they eventually date the sediments, and they're like, these aren't Ice Age. These are Pliocene, Miocene. They date from 7.5 to about 5 million years ago. They actually straddle the Miocene-Pliocene boundary and are part of 2 geologic epochs. And that's when they began to understand this is not an Ice Age site. We actually have lots of Ice Age sites in the East. This is a Neogene site. And why that is significant is from the maps I showed you last class period, we have very few Neogene sites in all of eastern North America. There's like one in Vermont, a couple in Florida. Otherwise, they're all out in the West. So this is a highly rare site. Now, at the time, Governor Don Sundquist was governor. He's the one that made this building possible that we're sitting in today. This is the Sundquist Science Complex, right? So Governor Sundquist gets word of this, and one thing happens after another, and eventually they decide this is such an important fossil discovery. It is of international significance. That's how important it is. So they set aside this site to become a brand new sort of fossil site, and it's preserved. And so they stopped the road improvement projects. Eventually, they'd go on to build a brand new center of excellence in paleontology, similar to how we have the Center of Excellence for Field Biology here. It is affiliated with East Tennessee State University. They got a big corporate donor to help support this. And now you can visit this place. It's an amazing museum, and it's got the fossil, all the fossil sites are right behind it, which I'm going to show you. So let's talk about how this site came to be. And it's a perfect example of reverse erosion. So about 7 to 5 million years ago, 7 to 3.5 million years ago, this site, which is in the Ridge and Valley of East Tennessee, was a sinkhole surrounded probably by an open woodland that was probably like a grassy, wildflower-rich woodland. But it also had lots of shrubs and lots of deciduous trees. It had some pine trees. But it had a sinkhole right in the middle of it, probably with some pretty sharp edges. And a lot of those, that served as a watering hole for wildlife. And they would come down and fall and sink to the bottom and die and drown in the sinkhole. Over the next few million years, you can imagine then the sinkhole beginning to fill up gradually with sediment. You know, mostly clay, because clay minerals are kind of settling into the bottom. There's some sand probably from nearby, sandy uplands. Also, there's charcoal. That's what these dark layers are supposed to represent, because there's wildfires burning in and around the landscape. Again, this is 3.5 to 7 million years ago. We had fire started by lightning ignitions. So the sinkhole continues to fill up. Again, occasionally we have more layers of charcoal being washed in from the surrounding burned uplands. And over time, you can imagine this very deep sinkhole filling up entirely. Now, I've been told that these paleontologists could spend 100 years digging and still never reach the bottom of the sinkhole. That's how deep it is, and that's how immensely important it is as a fossil site. So where does the reverse erosion come in? Okay, well, if you were to go to the site today, you would not see a topographic depression where the fossil site is. Instead, it appears as a hill. The sinkhole is now a hill today, not in the bottom of a basin. Here's how that happens. All the rock on both sides, so if I said there's a sinkhole there, what does that tell you about the geology of this immediate area?
Limestone.
It's limestone, right? Those carbonic acids in rainwater and groundwater have helped to form this sinkhole over time by eating away the calcium carbonate in the limestone rock. So that's how the sinkhole forms. It's a karst feature, right? Well, that limestone that is on both sides of that sinkhole is actually more easily erodible than the clay is that is actually in the sinkhole itself. That clay is so dense and so hard, that is actually harder to weather away. So on both sides, you can see limestone layers, bedrock, hard rock, and then that's that very dark clay that you see right there. Let me pop this image off. You can get an appreciation for just how dark that clay layer is. Now I want you to watch what happens over a few million years of erosion. It goes from being a sinkhole. Gradually, those surrounding uplands begin to erode through chemical weathering by the acids in rainwater and other mechanical weathering processes. But that clay is so erosion resistant that it forms a hill instead of a topographic basin. So that's the hill that they dug into when they were trying to improve the line of sight by the Tennessee Department of Transportation. They dug into the side of that hill and found that amazing fossil bed. Any questions about that? Kind of wild, isn't it? Who would have ever thought that clay would be harder than the surrounding bedrock? So the folks later on, they've now built an entire team around this place and a facility. They have their own faculty and staff and graduate students and research colleagues all across the nation who come to this site and study it. And they partner with renowned scientists all over the world, China, the United States, you name it. One of the things they've recently done is they brought in sediment cores, and they take these increment borers, and they're looking at, they want to date the sediments that are inside that increment borer. And they also want to look at like pollen samples that are deposited at different layers in that former sinkhole. This is from one of the recent studies that was published by Ochoa et al. 2012. And it shows sort of a physical relief map of the sinkhole. And you can see the areas in purple show where the sinkhole basins were located. Those black stars indicate the different places where they actually did an increment bore. They went down. They call these by different names. So they have like the bear pit, the elephant pit, the test pit, and the rhino pit. Those names obviously reveal something about what kinds of animals they were finding in this sinkhole. So now they didn't go very deep. They only went down a couple of meters at the farthest, right? The elephant pit's only 2 meters deep. You can see by the black horizontal lines, those are layers with abundant charcoal. Otherwise, these are finely laminated sediments, mostly clay formations, like you would expect in a pond or a lake. Also notice that there are the evidence of a few collapses of that sinkhole, as evidenced by the rock type breccia. Remember we talked about that, those angular rock fragments. So there are some breccia layers in here as well. Now, based on, and there is some conflicting evidence on ultimately what the immediate surroundings were. Some of the publications have speculated it was closed forest. In fact, the website of the Great Fossil Museum today touts it as being located in the densely forested Appalachian Mountains. Other publications, however, say it was closed to open woodland. Still others say it was a savanna with scattered grasslands. The jury is out on that. What we're going to do today is just look at some of the animals and plants that were there, and then we'll kind of talk about what makes sense. I think future research is going to be needed to kind of resolve what the surroundings were like. But this is a sinkhole pond shown from about 1907 in Northwest Florida, believe it or not. Check that out. That's a pretty dramatic landscape for Florida, isn't it? That's a big hill that goes down. That's a sinkhole, natural sinkhole right there, and with an open savanna woodland around it. This suggests what this pond could have looked like at one point in time. It might have been a little bit more densely forested than that. But notice that there is a grass layer on the ground. Fire would have carried easily across that grassy layer. Again, just to be clear, this is not the same site. I'm just showing you theoretically what it might have looked like. Now, what we refer to that is the original vegetation at the time this site would have been existing in the in the Pliocene is what we call the paleo vegetation. Here's a little bit of an excerpt. It says the paleo vegetation as a whole in the region might not have been able to reach its climax as a dense forest. So if you were to study vegetation ecology, one of the prevailing theories of 50 years ago or even 40 years ago was that vegetation proceeds in terms of what we'll call climax vegetation types. I'm sure most of you have been taught this a little bit. The idea being, imagine if you have an open field, right? What's the first thing that's going to come into that field from a succession standpoint? Probably some grass, right? And then what's going to come? Some shrubs, maybe some wildflowers. eventually the shrubs and some tree saplings, and then it's going to proceed very quickly into what? A thicket, and then a young forest, and then progressively over a century or two or three, it might become an old forest once again at some point. Most of us in this region of the country have all been sort of led to believe that everything naturally progresses toward forest, right? Except when you have what factors at play. What are things that naturally counteract the succession to forests? What prevents forests from fully developing like you might expect in the Smokies? Jacob, you got any ideas? What would keep forest from becoming a forest? Soils could, absolutely. Ken?
Fire.
Fire. What else? People, that's one. Logging.
Megafauna.
Megafauna. Those are the big ones I'm thinking of. Tornadoes, right? Avalanches. There's various things that could take down forests or prevent forests from existing at a given site. So one of the ideas then is that if you didn't have fire and big animals and people, some of these sites would probably progressively, progress into a closed forest, very shady, very dark. But the available evidence suggests it was probably somewhat open. You could see light would have reached the surface. Fires would have burned through, which indicates that it had to have fuel to carry fire, like grasses, for example. If that's the case, then we'll pick it up here. It may not have been able to reach its climax as a dense forest. That's that imaginary point at which everything progresses to forest. That's what we call climax. So what keeps it from going there is mainly because it was frequently under disturbance by abiotic factors, such as fires or drought, or another biotic factor would be large herbivores, megafauna. It is fairly clear that there is no modern vegetation analogous to the paleoflora that existed at this site. Basically, they're saying we can't find anything that matches what it would have been like during the Pliocene. That's why I put this picture in, because I wanted to give you something. And even this isn't a perfect match, right? Because red panda's not here in 1907 in North Florida. There aren't rhinoceros in North Florida in 1907. And many of the species are from East Asia. So there is no perfect equivalent. But I think structurally, this might somewhat capture what this site would have been like. So when we say that this is actually a fairly common term, that there's no modern analog, there's no modern equivalent to what we would have seen during the Ice Age or the Pliocene or the Miocene. If you study the paleovegetation literature, this is a very common phrase, no modern analog. And I want you to make sure that you're familiar with that. This is a different site. This is a place that SGI researches in Alabama. But maybe it was like this. Maybe it was an open oak woodland, maybe as opposed to say pine like this is, or maybe it was a combination in between. We know from the available fossil evidence that there actually was a lot of oak, pine, and hickory. So it could have been sort of a combination similar to these landscapes. This is another publication that talks about the reconstructed neogene vegetation at the Gray Fossil Site is a closed to open woodland setting with oak and hickory trees mixed with a diverse exotic climbing vines and shrubs, many of which have East Asian affinities, that thrive in a warm, temperate to subtropical climate. So the things like alligator would make sense in a subtropical climate. Now, finally, one of the ways that we can kind of get at this question and we can sort of evaluate this is by doing certain things like isotope analyses. So in addition, stable isotope analyses of bulk and serial samples of fossil tooth enamel from all of the ungulates at the Gray Fossil Site suggest minor differences in seasonal temperature and precipitation. What does that mean? They're looking at the ungulate animals, things like elephants and the rhinoceros. They're looking at their tooth enamel to determine what the environmental conditions would have been like. Now, that's a deep topic unto itself. I want to stop there just to let you know that reconstructing paleoclimate and paleovegetation often involves a deep understanding not only of geology and climatology, but also knowing things like the appropriate chemical analyses to evaluate the enamel of these ungulate animals that are there. That can reveal a lot about what the climate was like and what the vegetation was like. This is a aerial view of the gray fossil site. You can see that hill in the back that they're digging into. That is the process that has resulted from this reverse erosional process we talked about. There's an image of the rhinoceros skull right there in the bottom right. Now, according to a publication from 2009, it's thought that this was a small sinkhole about 2 hectares in size. It probably wasn't one sinkhole entirely, but it might have been like 3 or 4 sinkhole basins kind of loosely connected to each other, each with their own kind of pond-like, environment. But these preserved a very well-preserved record of sedimentation and fossils, again, that span from the Miocene to the Pliocene. And based on assessments of the soil that is deposited, they're able to determine, based on those soil profiles, that these soils and the climate is consistent with an area that has a monsoonal precipitation pattern. What that means is it's different today. We do not have a monsoonal environment. We have very regular rainfall that comes almost every month, okay? It rains almost as much in, the spring as it does in the winter, as it does in the summer. It's really equitably distributed here in this region. It's not so with West Texas or New Mexico or Arizona. Those are areas with a monsoonal rainfall. Now, I'm not suggesting it's like Bangladesh, right, where there's massive flooding and it rains all the time. That's not really what monsoonal means. Monsoonal means that the rainfalls come in distinct wet seasons, and it rains a lot at one time in pulses. So think about the desert Southwest, like Phoenix, Arizona. It may not rain a lot around the year, but when it rains, it may rain 3 inches all at once, and it floods, and you get flash flooding in the canyons and the streams. So it's thought that not only do we have sort of a warm temperate to subtropical environment here, but we also had a monsoonal precipitation pattern. So you would have expected long periods of drought, which would have favored things like wildfire, and then periodic bursts of rainfall. So more of a climate sort of similar with the American Southwest than with the current pattern that we have today. The seasonal climate may relate to changes in the ocean circulation pattern prior to 4.6 million years ago that resulted in an increased temperature and atmospheric pressure gradient between the east coast of North America and the Atlantic Ocean. This climate phase seems to be only a temporary condition, as underlying and overlying sediment are both consistent with drier conditions. So it was drier, it was warmer. Again, I point this out to show you that there's a broad array of information that can be gleaned from like the soils and the sediments about the overall site characteristics. Okay, let's dig in a little bit, literally. And here's what the fossil dig site looks like. Various paleontologists work in that site. This is what the inside of the museum looks like. You might know what these are. The animals in the upper right, over on the right side. You had to take a guess. What would that be? Say again?
Crocodile relative.
Not here. Now that's an alligator, right? Here's a rhinoceros in the back. So this is the tapir, one of those sort of snout-like animals. I'll show you an image of a tapir in a minute. Here's actually one right, where's the tapirs at? Right there on the far left. So based on now about 20 years of paleontological excavations at the site, an array of animals have been found, different kinds of elephants, saber-toothed cat, rhinoceros, flathead peccaries, these pigs that are more traditionally found in the American Southwest. At least a couple of species of extinct bear, like the short-faced bear, for example. Eurasian badgers, alligators, giraffe deer. I had no idea there was such a thing. And tapirs as well. So it's a great place. I wish it weren't so far away. We'd definitely take a class field trip. And of course, red panda, check that out, was also at the site. Now, I have included as a hyperlink here, a link to the species list that is known from the site. I encourage you to take a look at it, mainly for your own knowledge. And if you want to know more about an extensive bibliography of work that's been done, some great reading on the climate, the sediments, and the site chemistry, and lots of other discoveries by checking out that bibliography right there. Now I'm going to go through and show you some of the cool animals. I'm going to go through this kind of fast because I want to get on and make sure we leave plenty of time to cover the Ice Age in its entirety. One of the most heralded fossils from the site is Teleoceras epipsima, which is the barrel-chested rhinoceros. In many ways, researchers think that this was functionally very similar to a hippopotamus. That makes sense given that you got alligators at the site as well. So that hints at the fact that this very short-legged, very robust hippo or rhinoceros called the barrel-chested rhino, shown in the upper right and here again in the lower left, probably was semi-aquatic. It probably lived in water and was very much an aquatic type of mammal, similar to a hippo. There also at least is one species of elephant, possibly multiple. For a long time, they promoted that the elephants that were there, what they called the tree destroyers, what we call the shovel-tusk elephant, like Platybelodon, and that's shown here. Notice that those lower tusks sort of go straight out, right? Later on in the younger deposits, there are also mastodons, which are like a small elephant. In this scene, you've got ground sloth in the back on the right. You've got a peccary, which is a type of wild pig, in the lower left. And you've got various types of snakes. There's actually been probably about 10 different species of snake recovered at the site. Mastodons, the genus Mammut, are prevalent at the site. Just across the state line in Virginia, we have fossils of the Columbian mammoth from the Ice Age. So these are a smaller cousin to the mammoth. We had horses like Cormohipparion was the horse that has been described from the site. Tapirs, the ground sloth. We had a variety of things like camels, for example. I haven't been able to find a good illustration of the specific type of camel that was thought to have existed at the Gray Fossil Site. In the upper left is the giraffe deer, a strange group now that's completely extinct. They had like a collection of antlers coming off the top of the head in all different directions. Two different species of peccaries are also revealed from the site. And of course, today you can see peccaries in places like West Texas, Arizona. This is probably a related but extinct type of peccary. The short-faced bear, Pleionarctos. These are some of the big carnivores on site. Saber-toothed cats, the exact genus and species is not known. The bone-crushing dog, which is called Borophagus. These were known for crushing bones of their prey. Some smaller carnivores and probably omnivores like Bristol's red panda, which is the only incidence of red panda outside of China. The badgers that were here were more aligned with the Eurasian badgers that we see in Europe and Asia today. The earliest fossils of wolverine come from this place, East Tennessee. But strangely, you've got this mix of northern species. We often think about wolverines as being a northern species with deciduous forest species that actually rely on a lot of bamboo, like red pandas. And then put that with the species like the ringtail, which today is found in the desert Southwest and the arid Southwest, ringtails. So you've got this strange mix of things. And of course, you know, badgers, at least in North America today, are primarily thought to be a grassland and open woodland species. You definitely have other things that reinforce the importance of trees, like the giant flying squirrel, wetlands, such as an extinct type of beaver. You have a huge array of different rodents. There are even mole fossils at the site, various shrew fossils of multiple species. There's pack rats, there's birch mice, and there's at least 2 types of extinct rabbits. There's the long-tailed shrew, probably the same species as we currently have in the modern day. So that sort of testifies to the fact that both the long-tailed and short-tailed shrew, which are currently living species, probably were already present and evolved by roughly 4 to 5 million years ago. We have a type of aquatic shrew called the desman, which today is found primarily in the Ural Mountains of Russia, was found here. One of the hairy-tailed moles, and we have 2 bat fossils. Both have been identified as tricolored bat and big brown bat from these sites. There are beaded lizards, the Helioderma lizards, of which we have Gila monsters in the Southwest today. We're not sure if it's the exact same species or not, but that I think testifies to how dry and arid this region was. We have skinks, we have various lizards, we have glass lizards, which are often live in grasslands and savannas. We had alligators. So it's a real, and there's, by the way, that alligator skull from the site. We had xylant snakes, which are thought to be sort of like flying squirrels, right? They're gliders. One of the few records of that in North America. Coach whip snakes, which are common across the coastal plain in the Southwest. We had boa constrictors, sort of a holdover from when this area had more tropical species. And we had pine snakes at this site, which are definitely savanna grassland dependent species. So some of these species seem to cast doubt on the current findings and current sort of the current paradigm on the Gray Fossil Site's own website of characterizing this as just, hey, it's just your run-of-the-mill dense Appalachian forest. Well, I beg to differ, because species like pine snakes and so many of these others do not inhabit dense forests. They strictly avoid dense forests. So there's some, I think it points to the need. If you get too far down in the rabbit hole of just studying things from a geologic, paleontological, fossil perspective, it really helps to counterbalance that deep knowledge you need to have to be effective at your job with what? You need to know modern day ecology. Thus, the real need for people going into paleontology must be good at both. You really have to be. So you can have the appreciation, hey, I've got Pituophysis, I don't think I said that probably correctly, the genus that pine snakes and bull snakes are in. It'd be real helpful if you knew what modern day bull snakes and pine snakes need to survive, so then you could help better reconstruct, and that's called the nearest, what is it, the nearest living relative model in NLR is the approach that paleontologists often use. There are vipers at the site, not sure exactly which. There are water snakes, garter snakes, hook-nosed snakes. I'm not sure what those are. There are also hog-nosed snakes, various types of turtles, sliders, painted turtles, both extinct types. I love this one, this slider, which is an extinct type, unique to the site, with the mastodon blurred out in the background. Box turtles, soft-shell turtles, snapping turtles, all of these are present today. But take a look at the upper left. There's also the genus Hesperostudo, which are land tortoises, like we might expect in the Galapagos today, or the gopher tortoises, right? These live in sandy, open, dry ecosystems. Tortoises are a clear indicator of open habitats. And fossil birds, even flycatchers, various members of the oriole family, rails, turkeys, quail, and tropical birds like parakeets and parrots. Hawks, pygmy owls, geese, again, quail, sandpipers, ducks, all of those. And finally, even fossils of small amphibians, tree frogs of the genus Hyla, toads, spadefoot toads, tiger salamanders, dusky salamanders. What an incredibly rich fossil site from right here in East Tennessee. And I think it just shows how many of those things we still have with us today. but also how many things we don't. That's what I want you to get out of the Pliocene. It's a real mixed bag of things that we still have and things that have disappeared. Let's switch out now and talk about things from a some more from a plant perspective. Take a look at this leaf. This is a fossil from the gray fossil site. It's probably about 5 million years old, but we can compare this to the modern day, and it bears striking resemblance to the modern day cherry bark oak, Quercus pagoda, which is a species that is common around some of the deep south areas where you typically would find things like alligators and some of those species. There's also records here of other trees from the deep south, like bald cypress. There's a unique hickory here, which is related to pecan. It's actually been named the Tennessee hickory, Carya tennesseeensis. That's neat to think that those hickory nuts are actually 5 million year old hickory nuts. This is from your textbook. This shows a collection of Pliocene fossils from South Alabama. Again, very similar to the modern day species. And I'll show you just a few, like river birch. You could go to the Cracker Barrel parking lot and look at the planted river birch in the parking lot and hold it up side by side, and you cannot tell the difference. Same thing for that sweet gum there. Okay, very similar to modern day species. Now, I didn't have access to a lot of the leaf impression fossils. I wish I could see more of those. You'd have to go to the museum. They may have some digital collections that their researchers can access. I'm sure they do. Let's switch gears and look at another kind of pollen, another kind of fossil that they utilize to understand the paleo ecology of the gray fossil site. These are from those sediment cores that they did with those increment bores. This is fossil pollen from the same time period, roughly 3.5 to 7 million years, depending on the depth. They can identify most of these pollen grains, certainly to family, in some cases to genus, or in some extreme cases, even down to a particular group of species, like a species complex. So taking those cores from those sites, they were able to arrange these tables that have a lot of information on them. I'm going to focus in on one of them, and we'll kind of break down some of that information. So let's take the core from the bear pit. And number one, you can see just a representative image again of what they would be looking at. You definitely would have to be an expert in pollen grains. There's a whole science unto itself of studying pollen grains. And by the way, the name for that science is called palynology. And believe it or not, in many university departments across the country, a person who studies pollen grains, you think they'd be in a botany department, right? But they're usually in a geosciences department or a geography department. And that's because there's a very close amount of correlation between studying these. They're not necessarily studying these from a purely botanical perspective. They're studying these to help understand and reconstruct past climates and past geographic distribution of ecosystems. That's why a lot of those experts are in those departments to this day. So at the bear pit, notice then you have sort of over here on this axis is, I'm trying to think about this. Here are the relative abundances, right? So the length of the lines indicates how abundant it is at that particular sample point. I'm imagining that trying to remember what those numbers are on that axis. We won't worry about that. The key I want you to focus on, though, is I don't want you to get lost in the plant species names, because most of you may not have had a botany class, right? Those may not mean much to you if you're looking at the Latin name for some plant. They mean a lot to me because I happen to know that stuff as a botanist. What I want you to focus on are two things. One is, which are the groups that are most abundant? So why don't you guys call those out to me, first of all? Based on just pure numbers of pollen grains of that type, what's most abundant here? Pinus is certainly one of the top three, right?
Hickory and oak.
Quercus and Carya, right? Carya are hickories, hickory trees. Quercus are oak trees. Pinus are pine trees. And there's some other things in here too. There's ambrosia or the ragweeds. Asteraceae is the sunflower family. Ulmus is the elm family. Abies are fir trees. Poaceae is the grass family. Okay, and then we could go on and on. But the point there then is that the top three are hickories, oaks, and pine. In all three of those cases, those are trees that tend to be fire adapted, and they only really regenerate, meaning their acorns and their hickory nuts or their baby pine trees. Most of them regenerate having been adapted to fire. So you would expect some natural occurrence of fire on this landscape with those three being your top. Let me give you some other key takeaways as I see it as a botanical expert. Number one, dominant taxa are still common in the region today. There's still a lot of hickories and a lot of oaks and a lot of pines. So a lot of the things that are here, like liquid ambar, styraciflua, is a sweet gum tree. They're still there today. Number two, some of them are the same species, we think, that were present 5 million years ago as today, which hints that these species had already evolved by this time. So Tsuga canadensis is the eastern hemlock tree. And again, liquid ambar styraciflua is a sweet gum tree. That's very important information. Three, this suggests a mix of forest adapted species, closed forest, like a hemlock tree, woodland species like oak trees, and savanna species, lots of grasses, for example, or some grasses. There also still are some Asian representatives here, like Elaeagnus and Pterocarya. Pterocarya is an Asian member of the hickory family. Today, they don't occur anywhere naturally in America. They only occur in the wild in Asia. There are some elements here that are boreal, meaning they're found today mostly in the far north or up on the tops of mountains, like fir trees, for example. So this either suggests that it was cold enough for a fir tree to be down there with alligators, or it suggests that there maybe was an extinct fir species that had a broader range of ecological tolerances, that maybe wasn't always dependent on cold. Maybe it depended on warm conditions. We don't know of any fir trees today that do that. All the fir trees alive on the planet today are cold adapted fir trees. And then finally, there are some deep south species here, such as Taxodium, bald cypress, ephedra, which today you got to go to West Texas and New Mexico to see, or Utah. And then Cyrilla and Ilex vomitoria are both shrubs that we see today in Florida, South Alabama, and Southern Georgia. So it indicates that those are warm temperate elements that used to be here. Any questions about that? All right. Yes.
Do you know how they get those fossilized pollen grains out of the sediment core and onto a slide without destroying them?
Yeah, the first time I taught this class, we actually went to the University of Tennessee and they did a whole demonstration of that process. It's a very rigorous process. It involves a lot of nasty chemicals, a lot of acids and various washes that you have to do. You have to kind of follow, some very rigorous protocols that you would expect in typical lab procedure. You have to be sterile, you have to have a fume hood, 10 different chemicals. It's a rigorous process. And it takes a while. But basically, you have to go through the process of washing away the soils, and you have to isolate the pollen grains, which are tiny. They're micrometers in thickness. You have to preserve them because they are fragile to a certain extent. And then once you have them preserved and isolated, you have to get them onto a microscope slide. And you have to have them in numbers that are large enough to be counted, right? Imagine if your master's thesis was counting pollen grains underneath a microscope. You'd ruin your eyes, but people do it. So long story short is a very rigorous process. We're going to come back and talk about palynology in the next hour, because we are about now to transition out of the Pliocene. We're breaking into a completely new geologic period. Why? While it took a little bit of a catch up, there was a little bit of a delay when that Central American land bridge began to connect in sort of the late part of the Pliocene. It took time for that ice to begin building up in Greenland, right? But slowly with that buildup and the positive feedback loop, that ice began to grow onto the adjacent islands of northern Canada to Baffin Island and Ellesmere Island. And gradually, it also had more sea ice develop over the Arctic Ocean as an ice shelf over the ocean. And the more buildup of ice and the more buildup of ice, when that Central American land bridge connected, it sped that process up. And just in about 1.5 million years, we went from the conditions on the left to about 1.5 million years ago to having glaciers taking over half of North America. That, my friends, led us into a completely new geologic period called the Quaternary, and that's where we're going to pick up after we take a 10-minute break, and we'll be back here at 5:52. Okay, cool. We're going to start the Ice Age, 2 hours of Ice Age tonight. Man, I'm so jazzed up. I can't wait. Okay, so let's take a look at how we got to the Ice Age. Just one more repeat of that, and I know that the repetition gets a little bit old. But it's important to realize that the factors that were involved in putting the Ice Age in place, like if you were to go to YouTube, for example, and say, what causes ice ages, right? There are different ice ages through time. We talked about snowball Earth from 700 million years ago. The factors that created snowball Earth were different factors than what created the Ice Age, let's say, during the middle of Pangea, when Gondwana land was centered over the South Pole, right? That was a different reason. And then likewise today, in the past 2.5 million years, what has caused this Ice Age is due to different causal factors. Now, it is thought that Ice Ages within the last 2.5 million years are triggered by things that are in Earth's orbit, orbital irregularities with Earth's orbit. And I'm going to talk about that in a minute. Actually, I'm going to let a video do the talking because I'm not very well versed in astronomy. But we have to look there for some evidence as to how ice ages are triggered. But specifically for this last ice age that we're now still kind of a part of, it wasn't one event. It was a series of chain events that were put in place, really going all the way back about 35 to 40 million years, all the way back to about the Oligocene, the latest Eocene into the Oligocene. We can start sort of tracking in deep time the factors that put in place to create the conditions needed to stimulate and start this ice age. So let's just briefly reflect on those. Number one, roughly 45 to 50 million years ago during the Eocene, India collides with China to form the Himalaya Mountains. About 35 to 30, up to 25 million years ago, we also see the breakaway of Australia and the breakaway of South America from Antarctica. Both of those put in place that cold current which circumnavigated around Antarctica, creating the Southern Ocean and causing Antarctica to become shrouded in ice. Those factors cooled down the planet as a whole, right? The uplift of the Himalayas and the uplift of the Rocky Mountains, what did those two things do again? Rerouted jet streams, created rain shadows. They helped polar vortices to dive even further south, right? They rerouted the air circulation patterns. So what happens with Australia and South America is rerouting ocean circulation patterns. Those mountains are rerouting air circulation patterns. Okay. We have the glaciation of Antarctica itself as a factor. We have the Messinian salinity crisis. Remember, we talked about how the entire Mediterranean completely dried up, such that water then spilled over into the Mediterranean basin from the Atlantic through the Straits of Gibraltar. And that spillover was enough to greatly drop salt levels in the North Atlantic Ocean, which meant that the North Atlantic was less salty than it had been, and less salty water freezes at a different temperature, meaning that at the far northern latitudes, the North Atlantic was actually able to develop sea ice easier with less salt in it. And so that set the stage for the development of a polar ice cap over the Arctic and up in places like Greenland earlier than might have been expected because of what happened with the Messinian salinity crisis in the Mediterranean. And then the final nail in the coffin was the Central American land bridge connection, which really helped to cut off the warm currents and change those ocean currents once again. That was the final nail in the coffin needed to really start growing the ice pack up on the North Pole and the Greenland. And it took a while for that to catch up. That was the purpose of my last slide in the previous presentation. There was a delay, a lag time, such that over the span of about 1 million years, from roughly 3 million years ago all the way up to about 1.5 million years ago, that's how long it took for the ice cap to grow, covering down all of Greenland, eventually coming as far south as the modern-day Ohio River. Just 100 miles or less from us here in Clarksville was the southernmost edge of the glaciers that grew south during the Ice Age. All right, and then there's one more factor that's happening in the North Atlantic, which I have forgotten about now. So I can't remember why I put that last circle up there. That dates to last year, and I can't remember now. I think it was basically just saying the reinforcement of the buildup of ice was a major factor. Now, once we're in an ice age, and again, the run up to creating that ice age was 40 million years in the making. Once we're in the ice age, we don't just stay in an ice age for the last 2.5 million years. We go in and out of ice ages. So the Pleistocene is all about this very irregular experience. You could have been living 100,000 years ago. It could have been warmer than it is today here in Tennessee. It could have been almost, warm temperate. There might have even been alligators here. As you'll come to find out, we have no way of knowing, really. But the point is that once we hit the Pleistocene, it goes from cold or warm to cold, warm to cold, warm to cold, warm to cold. And that is a very regular process going in and out of warm and cold periods. We'll talk about what those warm periods are and cold periods are in a minute. But what causes us to change in and out of warm and cold periods once we're in the ice ages? That can be attributed to irregularities in Earth's orbit, which we call Milankovitch cycles. I'm going to let this video do the talking, okay? So we're going to watch about a 6-minute video that explains a fairly complex process of Milankovitch cycles. Before we do, I'm going to just preface this by saying a couple things. Number one, no, I'm not. I'm going to let the video do the talking. Okay, let's go to the video.
I find radiation from yourself on tumors.
I hope this volume is up loud enough here. Okay, that's one thing. We might have to gather around so you guys can hear this. I don't know why the volume on this is not very strong. Give me 1 second, guys. I'm going to stop sharing. I'm going to make sure I get the volume up as loud as I possibly can. We did this one day, right? Oh, it's right here. I'm good. I think that's it. All right, let's try this once again. Okay. Wait a minute. My friends on the screen can't see that, so I'm going to have to reshare. Okay. I'm going to test the volume out first, everybody, and see how that works. And then if the volume is good, I'm going to start it over at the very beginning, okay? Let's test it out here.
And dramatic changes to our climate. The ice ages have come.
I'm going to start it over.
And what's the price?
Can you guys on the computer hear this?
Yes.
All right, starting over right now. Here we go.
Over Earth's long history, There have been dramatic changes to our climate. The ice ages have come and gone. And what's surprising is that there's a strong pattern that explains why ice ages happen when they do. This is called the Milankovitch cycle. Named after Milutin Milankovitch, his theory explains how the Earth's climate changes over hundreds of thousands of years. His theory is based on two key ideas. First, the Earth's climate is strongly affected by how much sunlight the northern latitudes receive during the summer. Second, this amount of sunlight varies based on changes in the Earth's orbit and rotation. Why are the northern latitudes so important? It's because of ice. When sunlight hits the ground, most of the energy is absorbed as heat. But if the ground is covered in ice, most of the light reflects away because ice is white. This creates a positive feedback loop. Ice forms when it's cold, but ice also reflects light, making it colder, which forms more ice. So ice is really important for climate. The northern and southern hemispheres both contain lots of ice, but there's more ice in the north because there's more land. Land has a lower heat capacity than water, which means that water doesn't change temperature as easily as land does. This is why coastal regions are generally more mild and why ice forms more easily on land. Just look at the difference between the northern and southern hemispheres. In the south, there are ice caps that grow during its winter, but not nearly as much as they do in the north. During the winter, the land above the Arctic Circle is covered in darkness, experiencing twilight 24 hours a day. It's very cold, and lots of ice forms during the winter. And this is true no matter what's going on with Earth's orbit. The key variable here is how much ice melts during the summer. This depends on how much sunlight there is during the summer. Now, you might think that this doesn't change, but it does. Milankovitch showed that over hundreds of thousands of years, the amount of summer sunlight can shift plus or minus 15%. This can bring ice ages. This can end ice ages. How can the amount of summer sunlight be changing? Well, first, the distance from the Earth to the sun is changing. And second, the Earth's tilt is changing. The Earth's axis is currently tilted at 23.5 degrees, but this changes. Other objects influence the Earth gravitationally, nudging its tilt up and down. Every 41,000 years, it cycles up and down. When the Earth is more tilted, there's more sunlight during the summer. More summer sunlight means that more of our ice melts away. With less ice on the ground, less light is reflected away, giving us a warmer climate. Earth is unusual in that its tilt doesn't change very much. Earth has a very large moon, which stabilizes its tilt. Mars has two tiny moons, and so its tilt changes much more dramatically. The next effect is the distance from Earth to the sun. The Earth's orbit is not a circle, it's an ellipse. Every 4th of July, we celebrate aphelion, the day that the Earth is farthest from the sun. Then in January, Earth moves closest to the sun. Now the planets Jupiter and Saturn both nudge the Earth, causing its orbit to shift slightly, becoming either more oval or more circular. This happens over a period of 100,000 years. This effect is wildly exaggerated in this diagram. It actually looks more like this. You can barely even see that the distance to the sun is changing, but this subtle change has important consequences for our climate. Earth as a whole receives 6% more sunlight during January than it does in July. The seasons change because the North Pole sometimes tilts towards the sun and sometimes tilts away. The change in the distance to the sun, this works against the change in the seasons. This moderates the seasons in the north, since the Earth is furthest away in July. But this was not always true. The Earth's axis is moving in a circle. It's spinning like a top. This is called precession. In fact, I made an entire video about this. And what this means is that 13,000 years ago, the tilt of the Earth was reversed. When the Earth was closest to the sun, it was summer in the north. The distance change didn't oppose the seasons, it amplified seasons, making them more extreme. Now, warmer summer means more melting. More melting means less reflection, which means the climate as a whole is warmer. The amount of summer sun is affected by three long-term cycles. One changes the tilt. One makes our orbit more circular or more oval. And one changes how the distance to the sun matches with the changing of the seasons. These three cycles powerfully impact our climate. Scientists have measured the history of our planet using ice cores. Now, Earth's climate is complicated. You can't just reduce it to a single input. But the Milankovitch cycles have played a key role in our climate for hundreds of thousands of years. For more astronomical videos, please click to subscribe.
Well, I hope what that shows is that, one, what happens here on Earth sometimes is greatly affected by extraterrestrial events, right? I mean, we all kind of know that. I mean, we couldn't survive without the sun. We know that the moon influences the tides, right? But hang on, let me turn this off.
Video.
But how many of us would have guessed that, let me get this back on, then I'll resume my thought. Sorry. Let's stop this here, stop share, and then we're gonna go back. Okay. So, can you guys on the computer see this? Okay. Oh, I realize now that I need to drag that back. Sorry, guys. I really suck at this. Close that down. There we go. And now let's share. Okay. So how many of you guys would have guessed that something like Earth's orbit and the degree of tilt, right, and some of these other complicated things would be dictating whether or not we have ice ages or we don't? I personally would have to watch that video about 10 times, slowly, pausing it frequently, to reinterpret what it's saying in my own words before I really had a grasp on it, because I have not taken an astronomy course. So I would encourage you, watch it a few times. You know, I'm not going to test you heavily over that, but I do want you to at least be aware that the Milankovitch cycles, what the basics are and how it impacts whether we're in an ice age or not. And just know that the Milankovitch cycles exist. Okay, that's about as deep as we're going to go in Milankovitch cycles, but we are going to go much deeper in terms of the ins and outs of the ice age. Okay. Any questions before we proceed? By the way, there's a second video link there that builds on that first video, and I do encourage you to watch that. Clayton?
So if the longest Milankovitch cycle is oscillating 100,000 years, give or take, why do we not end up with way more ice ages over 500 million years? That's a lot of oscillations back and forth.
Well, keep in mind that the causes of different ice ages. So I don't think it's correct to say that the Milankovitch cycles drove us into this ice age, right? What drove us here was the past 40 million years of those other steps I called out, right? But once we were in it, whether we stayed in it continuously or whether we went in and out of it was caused by the Milankovitch cycles.
That swing the other way too, causing intense drought periods.
That I'm not sure, but I'll just say this, that, you know, keep in mind, Eocene was among the hottest times we've ever had on Earth. Miocene was still very hot. Pliocene was still very hot. So all those things were climatologically working against the possibility of the northern hemisphere being in an ice age. The conditions were not right. Remember, we had palm trees as far north as Alaska, crocodilian fossils as far north as Alaska. I mean, it was probably 20 to 30 degrees warmer, in some of the highest latitudes than it is today. So you had to have all those things first. And that's why you need the long view that I'm teaching in this natural history course of understanding how all these seemingly very different events happening all around the world are conspiring to put the elements in place needed to do things like cause ice ages, right? Which it also, I think, illustrates how we really don't know what the future holds in terms of climate change, in terms of climatic warming, human caused warming or otherwise. We just don't know. I mean, it could go any direction. It could be not so bad. It could be scary. So let's keep moving, but I wanted you to be exposed to the Milankovitch cycles. Now, next thing we need to do is let's focus on the fact that now we have these growing ice sheets. It's not just one, it's three. So we have three of these. The oldest one is the Greenland ice sheet, which today still exists almost intact. Almost all of Greenland is covered in ice, except for the coastal regions, which are tundra. You do have the Laurentide ice sheet. You need to remember that. And then if you're up in the Pacific Northwest and Alaska, areas to the west of, say, Alberta, Canada, would have been covered by the Northern Rockies sheet, which we call the Cordilleran ice sheet. And by the way, that term Cordilleran basically is a broad term. We can refer to the Cordilleran region as essentially the Rocky Mountains. 10% of Earth's water was locked up in glaciers during the Ice Age, compared to today just 1.7%. So a lot less water available in the oceans, which means that sea levels dropped dramatically. They dropped by 121 meters. So that means that places like Florida would have seen a dramatic drop in sea level. We'll talk about that specifically in a minute. Now, I'm going to acknowledge it, but we're going to come back and talk about it on Thursday's lecture when we begin Native American prehistory. That's where we're going to begin to reference the ice-free corridor, which some researchers hypothesized that some Native Americans would have come down through the ice-free corridor, which was open for a limited time during the ice ages. Others would speculate that they came by a coastal route using boats. And then still others think that it was probably some hybrid combination of the two approaches. But I do want to point out where the ice-free corridor is. It connects parts of northern Alaska down through Alberta, Yukon, and Alberta, Canada, into parts of Montana and North Dakota. This is just another way to visualize those three ice sheets we talked about. And then, of course, out over the Arctic Ocean is another ice sheet that is the sea ice. That's so important to things like polar bears and seals and other kinds of life. Now, I want to introduce four terms here for you, okay? There are glacials, which is the periods at which glaciers are growing and advancing. And then there are what are called interglacials. These are the periods where glaciers are fully retreating. Basically, it's the difference between being in a full-on ice age and in a time between ice ages, okay? And then the next term are what are called stadials and interstadials. Those are basically the growth of individual ice glaciers, either growth or retraction. And it happens sort of like this. Now I'm going to visualize this on the board. So just take a look up here. And for those of you who are online, I'm going to see if I can draw this in a way that you can see it behind me. Yeah. So imagine then you've got sort of here's Clarksville, right? We'll put that right sort of in the middle. Here's that. Here's the Mississippi River. Here's the Ohio River, okay? And let me fix this real quick. Now we've already talked about how glaciers at one time came down to approximately about where the Ohio River is. And about where like New York City is and then north, okay? So we'll put a couple of towns in here to help. I don't know if you guys online can see this or not. But like here would be Chicago. Here's
Oh, good.
Here's Cleveland, okay? Indianapolis would be about right here. Louisville, Kentucky is literally on the glacial boundary. And then this is Clarksville. So in a glacial period, that's that first term I want you to know, a glacial. The glaciers have moved south from the Arctic Ocean all the way to this point. The southernmost edge of glaciation period, because it changes over time, is called the LGM, the glacial maximum, okay? Excuse me, the GM is called the glacial maximum. That's as far as it ever went. The LGM is the last glacial maximum, meaning during the last period in which glaciers grew down, that's how far south that they came. And that depends on what point in time we're talking about, right? So the glacial maximum comes south, and then that tends to happen about every 150,000 years because of the Milankovitch cycles. So the glaciers advance all the way south. Then they go through stadials and interstadials while they're in that glacial episode. What does that mean? That means the glaciers here might advance a little bit, maybe a few miles or a few tens of miles over the span of a few years to the south. They're growing, okay? But that would be associated with the time of intensifying cold. But what happens if they begin to retreat? Right? Then the glaciers might retreat back. In some cases, dozens or even hundreds of miles, in which case we call that an interstadial. So this is a stadial, a period of growth of glaciers. And an interstadial is a period of the retraction or recession of glaciers. That makes sense? Now, what's the difference between a glacier and a glacial and an interglacial? Here is where that comes into play. If this glacier melts so strongly, so dramatically, that it pulls all the way back up into Canada, okay, and does so for a long enough period of time that it allows ecosystems, biomes to rebuild. Because remember, what's underneath all this ice? Nothing. Just scoured bedrock or just soil, right? So in its place, when these glaciers retreat, whole ecosystems rebound. The tundra vegetation that's immediately south of it moves back to the north. The taiga, the boreal forest, moves back north. The deciduous forest moves back north, right? Grasslands move back. So let's read this block of text right here. Generally, stadials endure for a few thousand years or less, interstadials for less than 10,000 years, while interglacials last for more than 10,000 years, and glacials for about 100,000 years. In order for a period to be considered an interglacial, which is what we're talking about now, it changes from Arctic conditions, like basically ice, through subarctic, which is tundra, to boreal, which is taiga, to temperate, which is deciduous forest or grassland, back again to Arctic conditions. So it has to go through that full range of change to be considered an interglacial period. It has to come from a glacial. It has to warm up so dramatically that everything goes back to being what it was, and then it goes back into a glacial episode. That's driven by the Milankovitch cycles, okay?
Can you have stadial and interstadial transitions within an interglacial period, just when it's glaciated?
Sure, yeah. I mean, you know, they're going to be what's called waxing and waning, right? They're going to be waxing and waning again, just like they would, except it's going to be happening in far northern Canada, and you won't be feeling it here. Yeah. Okay. So I wanted to cover that. That's an important set of terms you need to know. Now let's take a look here at this diagram on the bottom. Okay. This bottom diagram shows the past 650,000 years of time. So here's the modern day at 0. And notice that the red indicates warm periods. These are the interglacials where the vegetation is completely shifted back and forth through those changes we talked about. So you have what we are currently in, scientists believe, is actually just an interglacial within the ice age. We're still really kind of in the ice age, unless we screw that up with climate change and we sort of drive ourselves away from being in the ice age. So we're currently in what's called an interglacial, the Holocene interglacial. We have to go back about 100,000 years till we get to the next interglacial, the Sangamon interglacial, named for the Sangamon River of Illinois. Then it's about another 100 years back to the next one, right? Think about the Milankovitch cycles and the periodicity of those. And you can see we go back through time, and these are separated by the cool events shown in blue, which are the glacial episodes. Now, we have, scientists have named these different glacial episodes. The last one is called the Wisconsin glaciation. The previous one was the Illinoisan. The oldest one was the Nebraskan. And then in the middle, we don't know. And the reason we don't know is because every time there's a new glaciation, it acts like a big bulldozer and it totally obliterates the ones before it. Mostly, not always. But these right here, we have a lot of deposits of both the Wisconsin and Illinois still around. We have a little bit of Kansan age. We have just a tiny bit of Nebraskan age of deposits. But all the ones in between have been so obliterated and bulldozed. We really don't know how many glaciations there were. The only thing we can do is connect it to the ice core data, which we can get from Greenland, going back 650,000 years. And the ice core data is what reveals these ups and down patterns in Earth's temperature. And that's also can be judged by using oxygen isotope data, looking at oxygen-18 isotopes. Okay, we can also look at carbon dioxide, by the way, because carbon dioxide mirrors oxygen-18 isotope data. Both of them serve as a good proxy for estimating temperature. Any questions about these different glacial periods and so forth? Okay, let's just take a look at that a little bit deeper. So again, we've already talked about that changeover during an interglacial. It goes from Arctic conditions through subarctic tundra, boreal taiga to deciduous temperate forest, and back again. That's what constitutes going into an interglacial and back. Pretty dramatic changes. Believe it or not, we're going to spend a lot of the second half of the last hour class, especially talking about those changes with respect to here in Tennessee. Now, we've never been covered in Arctic ice, but we have had subarctic. So the subarctic, the taiga, and the deciduous forest were all three different types of major ecosystems present here as recently as 18,000 years ago.
When you say that they transition back,
Yeah.
right, does it go deciduous taiga, subarctic, Arctic, or does the ice grow fast enough to just bulldoze a taiga?
Oh, sure. Yeah, I mean, the growth of the ice is happening at a frequency to where a lot of your more common species can disperse ahead of it, right? Research has shown that, beech trees and hemlock trees can disperse, in response to cooling temperatures, a few hundred miles in the span of about 5,000 years. So there are some species that can move. But the sedentary species, the ones that cannot move, are driven to extinction or localized extirpation. That's why the Southeast has such a high rate of endemic species that occur nowhere else on Earth, because we've never been covered in glaciers, not since snowball Earth 700 million years ago, right? But these kinds of rapid changes, yeah, some things can move, but some things cannot. That's an important part of the whole story. Any questions from my friends online here?
Doing good.
Okay, good deal. All right. Now, let's take a look at how the 4 glacial episodes that we know about map out onto the American landscape. Number one, take a look at the largest area. That's the most recent glaciation, the one from the past 100,000 years. We call, by the way, here it's called Wisconsin. I've always learned it as, add an extra AN on the end, the Wisconsin glaciation. I've been corrected on that by a few professors. So I prefer to call it the Wisconsin glaciation, and I think you should too. I can't tell you why. The Illinoisan, the Kansan, and the Nebraskan. So this one in beige came to New York City, came down to Louisville, Cleveland, Chicago, Milwaukee, Minneapolis, Pierre, South Dakota. These were all cities that were under 3,000 to 5,000 feet of ice during the last glacial episode. Who knows when the glacial maximum reached this line? How far back in time do we have to go to get to this this line at the southern end of the beige zone here? Anybody know? How far back in time? It's the youngest of the glaciations. How many? 100,000, give or take. Let me ask you another question. Were there people in America when the glaciers were a mile thick over Cleveland, Ohio? When there was no Great Lakes because it was covered in a mile of ice. Were people here? Yes, indeed. People had conclusively been here in America for at least 21,000 years. That glacial maximum that you see, that line, is 18,000 years old. That's how young it is. There were people definitely living in, say, New Mexico at 21,000 years. Arguably, people could have been here as old as 40 to 50,000 years, although that gets really, really hotly debated. Now, so what about those other ice age events? So Clayton, to get back to that ice age would have begun about 100,000 years ago. And it grew and reached its eventual southernmost point. Remember, it started growing way up near Greenland, right? It grew and reached its southernmost point here 18,000 years ago. Then a Milankovitch cycle kicked in, or maybe we're in an interstadial, right? Because we're in the Holocene interstadial, or do they call it interglacial? Excuse me. Holocene interglacial, right? So we're now going into a period where the glaciers have retreated all the way back up to Greenland, right? So yeah, that spanned from about 100,000 to 15,000 years ago. The ones that came the farthest south are this next one, and you see it's the Illinoisan. It came all the way down to Carbondale, Illinois, to the Ohio River at Louisville, Cincinnati, and it barely actually crossed into Kentucky. So a little bit of Kentucky was glaciated, but that one happened about 200 to 125,000 years ago. Next, we have those that were 550 to 250,000 years from the Kansan. And these are found especially in northern Missouri, eastern Nebraska, northeast Kansas. And then the one that is the oldest, that we barely have any at all left over, is the Nebraskan. And that is the one that is in Nebraska. It barely pops out in just a few places up in here where that purple line is right there. And you can see what I mean by the fact that it was covered up by the next youngest glaciation. It basically bulldozed over. So that obliterates. It obliterates landscapes. It flattens hills into plains. It fills in river valleys and clogs them up or reroutes rivers. It causes fossil records to be obliterated and pulverized. So that's why we know very little about life in the early to middle ice ages, because everything's been really lost from that time period, from that area of the country at least. Okay, and again, that's the GM or the glacial maximum line we talked about. Okay, let's switch gears real quick and let's go back and talk about these climatic fluctuations that are happening during the ice age. The Greenland ice cores help us go back in time 650,000 years. Here's a team of scientists that are drilling various places on the Greenland ice sheet. And notice how deep some of these are, 3,230 meters. In the case of the deepest ones, what's called the grip. There's some other ones that are quite deep. These cores then are stored long-term, places like the University of Maine, for example, and they're analyzed and funded by some deep research dollars like the National Science Foundation, the National Oceanic and Atmospheric Association. These cores then are dated. They're subjected to many types of analyses and studies. They're looking for they're looking for gas bubbles in these cores so they can determine what was the concentration of carbon dioxide. They're looking for oxygen-18 isotopes so they can determine what the ocean temperatures were and the ice temperatures were at that time. All of that in a complicated way, and it's more complicated than my brain can comprehend at this moment. But a lot of chemistry is involved in understanding these kinds of fluctuations. So you can imagine if you have an interest in these types of subjects, you need strong background in biochemistry, or you need to collaborate with chemists who can inform those aspects of your research collaboration. I would encourage you to study this and read up on this. I'm not going to go into this in any more detail. But I do, it might be helpful so you can just sort of see the general relationship of these oxygen-18 and first 16 isotopes and how they get some of that information from them. A lot of the books that I've studied and that I rely on to build this class have extensive chapters dedicated just to this topic. So it's a big deal. And if you're interested in going into this, I would encourage you to read up on this a little bit more. Okay. There's some other, this fairly complicated diagram, I'm going to just simplify it. This is just showing a shorter span of time, about a 400,000 year period, using the Greenland ice cores again. And in addition to the oxygen-18 isotope data that we can glean what the temperatures were like from that isotope, we also have methane gas that can be assessed from the ice cores. We can use that to look at temperature. All these can be used to assess temperature. And then we have things like carbon dioxide concentration as well. This shows today, based on just carbon dioxide alone, this is the patterns of all of these things. But notice that methane gas and carbon dioxide, if you carry those forth into the future a little bit and based on present day, those have really spiked based on the current output levels from fossil fuel burning, which if we go by this and we look at the correlation between greenhouse gases and temperature, you can see the correlation. It's very tight. This has been analyzed statistically. If we all of a sudden see massive spikes in greenhouse gases, it does beg the question, what is eventually going to happen to our temperature? You would expect them over 650,000 years of data for temperature to also spike. How much, how fast, we don't know. That's part of the unknown. Okay, with that, let's see what time it is. I'm going to go one more slide and we're going to take a break after this. Let's cover some of the key moments in the Pleistocene's chronology, okay? This is from one of my favorite books that I studied as a PhD student, a book published in 1999 by Alan Graham at the Missouri Botanical Garden. It's a complicated book, and it took me a long time to get through most of it, but it was really instrumental for me, developing this class, and for me developing a lot of my sort of concepts as a scientist. It's very heavy in paleobotany, just be advised. But if you are pursuing or interested in pursuing a career in paleoecology, paleobotany, botany, etc., I would definitely advise you to check it out, or paleontology. So here's some key events. Let's just focus on a couple. One, the onset of significant northern hemisphere glaciation, again, stemming from the closure of the Isthmus of Panama, has been well reported. And again, that goes back to roughly 2.7, 2.6 million years ago. But the actual onset of the ice age, some people attribute that as being roughly 1 million years later, right? There's a lag time you would expect. So 1.7 million years is given by this paper from 2004. Again, we use this. There's some debate about when to set that, but that's sort of not anything we need to get into. Another key event is some of the when the last glacial period ended. We covered this a bit ago, 130,000 years ago. Then we went through that interglacial period. By 118,000 years ago, we begin the Wisconsin glaciation. Again, just thinking through this, I don't necessarily want you to memorize this stuff. I just want you to think about sort of the story and the sequence of events. So we were in that glacial period for a long time. Remember, things were growing from 100,000 years ago. They were growing all the way south till 18,000 years ago, they reached here. That's not to say they grew continuously. Remember, during that glacial period, they went through stadials and interstadials. There were brief pauses in growth. There were periods where they went through pulses of growth. And there were periods where it warmed a little bit and the glaciers pulled back, maybe 100 miles or more. But then they grew again. They pulled back, grew again, pulled back, grew again, right? Those are the stadials and interstadials. But eventually they grew all the way to the south, and the Milankovitch cycles caused them to switch back and grow back to the north. That's the interglacial and glacials that I want you to be familiar with. Okay, so the last glacial maximum was between 23,000 and 19,000 years ago when it reached its southernmost point this last time. At about 19,000 years ago, we see an abrupt rise in sea level. So what does this do? This cuts off the Bering Strait. That means if the ice-free corridor hypothesis is correct, there was a limited window for people, for Native Americans, to migrate from Siberia into North America along the land bridge corridor. So this has been fairly well timed out, and there was limitations, not only on the availability of a land bridge through the Bering Strait, but also they had to have an opening in the ice. Both of those have been separately dated, and they both had to be in effect for that corridor to be able to be useful. So again, an abrupt 10-meter rise beginning about 19,000 years ago as the glaciers began to melt. Humans possibly present in the southeastern US by 19,000 years ago. There's been a slew of, and we're going to get into this next week, possibly on Thursday, looking at some of the evidence for Native Americans from 14, 18, 16,000 years ago. We now have conclusive evidence, at least 21,000 years ago from New Mexico, from the White Sands National Monument, of people. And then there's a whole series of events leading to climatic instability. Some of these, like the Bowling Alderod warming period, happens abruptly. We're talking about very quick changes, over the span of hundreds of years, maybe a couple thousand years or less, where massive changes are happening. Glaciers are calving off icebergs into the Atlantic. Massive amounts of meltwater are pouring down the Mississippi River. The Mississippi River would have been 4 times the width of its current width. Lots of changes happen. This is also at 14,500. Now, keep in mind, this is from the 2000s. That's the oldest credible evidence of humans in Florida as of that date. At 12,000 years ago, we go through a rapid a rapid cooling phase. We had been warming, and then we go right back to a cooling phase. And that is triggered, my friends, with the largest extinction event we've seen recently. That's when we see, shortly after, around 12,750 years ago, we see the extinction of most of our megafauna. Ancient bison, longhorn bison, woolly mammoths, mostly. Some of them lived on Wrangel Island or some of the islands off the coast of Russia till about 3,000 or 4,000 years ago. But most of the big animals, the big carnivores, went extinct during the Ice Age, and we're going to talk about it in the last hour. And finally, about 12,000 years ago, that Beringian land bridge is completely flooded. And so these are just a few dates that serve as a prelude of what's to come. We're going to talk about a lot of these events over the next 2 lectures, including some in this final hour. And then the Younger Dryas cooling event abruptly ends by 11,570 years ago. This is roughly considered to be the break between the Pleistocene and the Holocene. Okay. After that, we go into the Holocene epoch, which is the period that the epoch that we're currently in. All right, so let's stop there. Let's take a break. We'll come back at 6:53, and we're going to pick up with the remainder of the Ice Age. We're going to focus more on what were some of the Ice Age critters living during this time period. That it'll be cool to show you some of those. Okay. Okay, so now let's switch gears and let's look at what was the impact or the effect of glaciers on the American landscape. Okay. Now, let's also say that obviously the effect of glaciers here in Tennessee was very different than, say, Quebec, Canada, right, or northern Minnesota. One of the ways that they were different is that southern Canada and probably not even just a bare tip of northernmost Minnesota were in a different zone called the zone of erosion. And that means that everything there was completely scraped almost down to bedrock by the repeated glacial events of the past 2.5 million years. So that's the zone of erosion. Well, what happens when you erode something? That something has to be deposited elsewhere. So south of that red line, and over here, by the way, the zone of erosion largely coincides with the St. Lawrence River. I just didn't draw it. But south of that line, you enter what's called the zone of deposition. That's where all that glacial debris, the pulverized rock and what's called till sediments and moraines were ultimately deposited over large swaths of the Northeast and Midwest. Not here. We've never been covered with glacial debris here. Okay, so zone of erosion and zone of deposition. Here's what a glacially eroded landscape of Canada looks like. This is probably up in like Ontario. You can see lots of glacial lakes and there's lots of exposed bedrock. It's all part of the granites of the Canadian Shield. A lot of igneous rock there. And this is what it would have looked like after the ice had retreated. It would have left barren wastelands that then had to be recolonized by tundra vegetation and taiga and temperate forest in some cases. So that's tremendous potential for ecosystem, biome level rebound in these landscapes. Notice the evidence of where the glaciers have dragged across that landscape, right? See the lines where they carried those rocks and boulders? And every time they had a rock trapped underneath that ice, grinding across the land, it basically wore grooves into the bedrock. Those are still visible in places like Central Park, New York, right in the heart of New York City. You can see the glacial groove marks if you know where to look. Then the zone of deposition is where all that stuff was deposited or laid down. And it happened in a very complex arrangement that can be dated. We can know when a given glacier of the Wisconsin glaciation covered, let's say, a particular section of Ohio or of Wisconsin. And you can see how they moved almost like in, concentric, sort of concentric rings, right? Moving south, for example, or actually it would be the other way, retreating from the south back to the north, leaving these piles of rock debris and soils from these glacial landscapes. Now, in the on the right is a map of Ohio that shows the glacial boundary, the glacial maximum here. The southeastern portion of Ohio has never been glaciated. It's an unglaciated region, just like all of Tennessee. The northern and western halves of Ohio, however, have been glaciated. And one of the things that we can see on that is the parts of Ohio that have been covered in the various glaciers of different ages. So there's Wisconsin glaciers that cover down to here, right? That's these, the different colors in blue and green and beige. But even older than that, way back in the Illinoisan and pre-Illinoisan glaciations, would have come all the way down to the Ohio River. That's the oldest glacial deposits. The ones that came into Kentucky were pre-Illinoisan, pre-Wisconsin glaciations. So hundreds and hundreds of thousands of years old. Now, there were glacial deposits south of the glaciated region. take a look at these rivers, right? That's where you had glacial outwash. So as the glaciers were calving off icebergs and melting, they were generating rivers and streams. Or in some cases, as I'll explain in a minute, they were actually blocking stream channels. But in these cases, that glacial meltwater had to go out somewhere, and so it went down stream valleys and river valleys, carrying with it boulders, we call it erratics, cobblestones, gravel, and all kinds of other sediments. And that's what we call outwash sediments. And that's what makes up today the Pleistocene Valley trains of the Mississippi floodplain north of Memphis. So we do have glacial outwash sediments in Tennessee. And here you can see where they're tied to these stream valleys that were being part of these glacial meltwater streams. Now, there's a whole system of glacial landforms. We don't live in Ohio or Illinois, or otherwise we'd probably spend a whole lecture talking about glacial landforms. But I do want to divert your attention up here to the upper left, and you can see some of those. Let's talk about a couple of them, all right? Number one, when a glacier advances, in this case, southward, it is pushing and acting like a bulldozer. It is flattening hills and pushing, rock debris and filling up stream valleys. And then as it's pushing, there's a lot of stuff trapped under it, which is called the ground moraine. It basically drops all that stuff underneath it. That forms a layer of sediments called glacial till, which is parts of fragments of rocks of different sizes and different kinds of rocks and sediments and gravels and cobblestones. That's all the ground moraine. When the glacier stops at a given point, particularly as it's retreating or at its very, very southernmost tip, it drops a big pile of debris that forms a long linear hill. And that's called a terminal moraine. Okay. Sometimes these can be 50 or 100 feet high on the landscape. They can be very obvious features. But if a long time has gone by, they can be eroded down and they can be barely perceptible. Then there are all these other kinds of things like cairns and cames and drumlin fields and kettle lakes. All these are different, and eskers. These are all landforms associated with glacial landscapes. So if you live in Ohio or parts of Pennsylvania, Illinois, you may be interested in those. So I would say go to the back half of the PowerPoint, and I've got an appendix 1 with a collection of about 10 or 15 slides dedicated with photographs of some of those glacial landforms if you're interested. And here's also some websites that are helpful on understanding glacial landscapes. All right, with that though, so last thing I'll say, you can see then all the areas in beige on this Ohio map are the ground moraine where glaciers covered and dropped things underneath the glacier. And the green concentric rings are the terminal moraines. So these would be lines of hills, right? That form, and these are really important features to know about on the landscape. If you work for the Ohio Department of Natural Resources, moraines are really important because just the difference between being out here on the ground moraine versus being on one of those terminal moraines, it's a different landform. There may be bogs here. This may be an area that's high and dry with a rare type of oak woodland, there may be groundwater that seeps out of that terminal moraine that forms a rare wetland type that's home to rare invertebrates or rare bog species. So it's really important if you're in these landscapes to understand that glaciation has impacted a lot, and you should become as familiar as you can with those landscapes. Now, not everything in the Midwest was glaciated. In fact, there's a big region that I should change the color on this, shown here in this outline, that was never glaciated in all of the past 2.5 million years. And I want you to notice how, looking at this, it looks like it's very topographically dissected. In fact, if you were to look over Middle Tennessee, you'd see all those stream drainages, right? Those river corridors. It's a very hilly region in southwestern Wisconsin, southeasternmost Minnesota, and parts of adjacent Iowa and Illinois. That's a region we call the driftless zone because there were no glaciers that covered that region. This shows how the driftless zone sort of formed. You can see the big lobes of the Laurentide Glacier moving around both sides of it. And this happened repeatedly throughout the Illinois and Kansas and Wisconsin and glaciers. But somehow that region was just never covered with glaciers. If you were to go there today, it looks very much like parts of central Tennessee. Very hilly, beautiful, forested, rugged. Those hills have never been flattened by glaciers. They still have the same bedrock geology that they've always had. A lot of that's Ordovician rock, Silurian rock, Devonian rock, Mississippian. The same kind of rocks that we have here in central Tennessee and Kentucky in an unglaciated area. Now, we're of course down here, right? This is up here, this unglaciated driftless zone. Now I want you to look at what's in between. And this is going to give you an idea of what this used to look like and how much this landscape has changed. Remember, when a glacier comes across this, it can pulverize rock, it can obliterate hills, or it can fill in valleys with glacial till, right? So this can go from a very rugged, hilly terrain to what? A flat plain. If you've ever driven to Chicago, you go through what's called the Corn Belt. Almost so flat you can't stand it, right? Just about like this table. But it wasn't always that way. Prior to the Ice Age, central Illinois, if you go down far enough beneath the cornfields of Ohio and Illinois, and this would be true probably of eastern Iowa, there were all the signatures of hilly landscapes underneath it. They've been covered up and flattened, or covered up and pulverized, or covered up rather with these flat plains that are called glaciated plains. And so that's the difference between a glaciated landscape and an unglaciated landscape right there. Now, by the way, on this, I've also indicated, here's a few places where even on Google Earth, you can make out the moraines if you know what you're looking for. You can see them sometimes. Some of the evidences of glacial landscapes include things like erratics, where these giant boulders have been inexplicably just dropped in the middle of nowhere. Those were carried by ice and left when the glaciers retreated. The striated bedrock we talked about, places like Central Park, and glacial till, which is this sort of amalgamation of different types of rocks and soils of different types. Okay, now that's a little bit about the changes to a glaciated landscape. Let's look at what happens when glaciers impact unglaciated landscapes like Tennessee and Kentucky. Well, number one, when those glaciated landscapes, when the glaciers retreat and it's a barren wasteland, you can have very strong winds that pick up along the glacial front called adiabatic winds. And these winds blow very strongly as a sort of gale force winds. They pick up all this recently pulverized rock that is rock flour, and they blow it through these wind-blown processes we call aeolian processes. And these aeolian processes, shown here, can lead to the redeposition of those wind-blown rock flour sediments that we call what? It's called lust deposition. And so this is just an image here showing soil being picked up probably from some farm fields where they plowed on a windy day. And, you know, this is a good way to lose topsoil. This is why we shouldn't be plowing fields anymore. We should be using no-till drill approaches to planting agricultural fields, because we're losing large amounts of topsoil to erosion. But this, again, is just mainly to exemplify sort of what we might have expected with lust being picked up and redeposited elsewhere. So what was the impact of that lust being blown from places formerly covered in glaciers? Where did it go? A lot of it covered both existing glacial landscapes, like where the glaciers retreated, but it also was blown into places like Tennessee that had never been glaciated. Here's an image here just to show. You have this area covered in ice. You had these winds that were coming off the glaciers, this glacial cyclone, anticyclone, or what we call adiabatic winds. And this was helping to pick up and drive those very forcefully into other places. If you look at this map, this shows the areas of significant wind of lust deposition across the center and upper northwest United States. And notice here then, on the right, you can see the relative depth of some of those. Now, there also were sand dunes that were blown up across Nebraska. We call the Nebraska Sand Hills today, one of the largest areas of remaining prairie in the country. But particularly the deepest parts of lust deposition occurred on the eastern side of rivers. So along the eastern side of the Mississippi River, we have this deposition of very deep beds that are greater than 20 meters in thickness. Along the eastern side of the Missouri River, across the river from Omaha, Nebraska, great place to see them from the city of Omaha. And then at various places along like the Platte River and some of the rivers in Nebraska. But notice that even while the depth of this lust, which forms an entire ecoregion, you remember the name of that in Tennessee and Kentucky? What is that level 4 ecoregion that extends as a bluff along the eastern side of the Mississippi River? It's called the Bluff Hills ecoregion, or the Lust Bluff, right? But even to the east of that, over Clarksville and parts of like Dixon, south of town, we had this thin veneer or mantle of lust, which blew across and covered like a blanket all of western and parts of west central Tennessee. Now that lust is so fragile, it's so easily disturbed and erodible that, you know, as we plow that, it's easily lost. It blows away in the wind. That's how fragile it is. So a lot of that lust deposition, if you know where to look, you can see it. How many of you know where Trenton Road is up on the north side of Clarksville? There's a place when you go north of up on Trenton, you cross Needmore. And if you go just north of there, there's an apartment complex on the left. And you go just a little bit to the north before you drop off into the valley of Spring Creek. If you know what you're looking for on the right, there's a little bit of an exposure of soil along the road. And you can actually see a deposition of lust that's about maybe 6 inches to a foot deep that forms the cap over the soil layer there. Okay. Now, here's how that lust can look. This is a lust deposit in West Tennessee that is, I think it's like 17 meters thick, something like that. Here's a lust deposit on a bluff above the Mississippi River in Illinois, up near Cahokia, Illinois. You can see that big, dense lust layer on the top of those Mississippian-aged limestone bluffs there. All right, so lust formation can be important. A lot of that lust is rich in calcium. It was pulverized parts of limestone out in the Great Plains. And so that lust deposits in places like Memphis now. There is no limestone there, but the lust itself brings calcium carbonate, which makes those bluff hills a calcium-rich region. So you can get trees and wildflowers and other species that normally would grow only on limestone. They grow in the bluff hills forest because of the richness and calcium that's present in those. All right, let's talk about buried streams, ice dams, and proglacial lakes, okay? Most of you have probably heard of the Taze River, right? Anybody ever? Raise your hand if you've never heard of the Taze River. Well, okay, maybe most of you haven't heard of it. So the Taze River is an extinct river system that was thought to have begun. Originally, it formed what is now the uppermost new river of North Carolina and Virginia, which is considered to be one of the oldest rivers on the planet. The New River crosses around where Roanoke, Virginia is, goes into West Virginia, where it becomes known as the Kanawha River. And then it flows through a few mountain valleys, crosses over the modern day Ohio River, and actually goes into Ohio. And at that point, and by the way, you can see the old abandoned river channel in Ohio. It does not have a river in it today. So that's a clue that, whoa, there used to be a giant river here, but there's no river there anymore. Where it is in West Virginia and Virginia, it has the modern day New River and Kanawha River flowing through its original channel. But when it hits this, it just disappears. It disappears into the glaciated plains of southern Ohio, which tells you that that entire landscape has been pulverized and buried. And the thought is, and by the way, they've been able to pinpoint where the river was by, using various types of sonar type measures. And they've been able to tell that the Taze River once went over and reconnected with the modern day Illinois River near Peoria, Illinois, where it reconnected down to the modern day Mississippi. So that river used to flow north, northwest, and west. Glaciers came, they buried the channel entirely. And what do you think the effect of blocking up a river would be?
Pretty serious impact because of that.
Yeah, I mean, number one, you got a glacier there now where there was none. So it's changing the temperature at the edge of the glacier dramatically, right? So whatever was here vegetationally has either moved or has gone extinct or locally been wiped out. Now you've got a fringe of very cold temperatures adjacent to that glacier. So that means you're probably going to develop tundra right at the edge. You have shifts in vegetation. Everything has to shift south. The river is either going to be backed up, it's going to reverse, or it's going to be more likely flooded, right? And so what happens when you flood the ancient Taze River? It forms a lake, an enormous lake, right there at the glacial front because the ice is backing up the river, right? The ice has cut off its flow. So then all these valleys back behind it, in parts of West Virginia, near Parkersburg, West Virginia, and southeastern Ohio, all those valley lands begin to flood and become inundated with 200, 300, 400, 500 feet of water. This includes parts of northeast Kentucky. This glacial lake, by the way, is called a proglacial lake because it's pro meaning sort of on the front end or the leading edge of a glacier. It's called Glacial Lake Tigt, T-I-G-T. It has a name. Now, notice then, there's also a glacial lake, very likely in the Mississippi River Valley over here. We'll come back and talk about that one in a minute because allows us to make certain discoveries that would not have been possible otherwise if a lake hadn't been there temporarily. And then finally, this map is incomplete because it also, what would you predict about other glacial lakes based on this map? Where should there be some more backed up proglacial lakes? Exactly. So that's exactly what we see. Some of the recent publications suggest that there were ice dams in multiple rivers like the Allegheny and the Monongahela, and some of these other rivers of northern West Virginia and adjacent Pennsylvania were blocked up, meaning that much of western Pennsylvania was underwater in those mountain valleys around Pittsburgh. Pittsburgh would have been under quite a bit of water at that time. That's pretty cool, isn't it? I mean, that's one of the coolest things I can think of. The sediments testifying to the presence of these lacustrine sediments is what they're called, by the way. Lacustrine. Lacustrine sediments are lake sediments that lay down, and people who know their sediments can recognize lacustrine sediment because of certain kinds of features or certain types of organisms like aquatic snails. And these are present in those mountain valleys on the sides of hills in some cases in West Virginia and Southeast Ohio. All right, let's go back to real quick those ones from the Mississippi River Bluffs and the Bluff Hills just north of Memphis around Meeman-Shelby State Park. There are some loess deposits there, which are windblown, aeolian. But if you go down below, embedded in some of those, in certain layers, if you know what you're looking for, are lacustrine sediments that date to about 18 or 20,000 years ago, and right at the last ice age. And from those, we can study pollen grains and aquatic snails. And that helps us to understand what the ice age environment near Memphis was like at the very end of the ice age. All right, I've got this diagram here. By the way, here's the modern day Ohio River, right? Here's Huntington, West Virginia. This is Kentucky. Here's Ohio. This is the modern day Ohio and its floodplain. And then this is that anomalous sort of ancient isolated floodplain that had a big river flowing in it that is no longer there. So for those of you on the computer, this is the ancient Taze River Valley right here. So again, the implication is an ice dam, basically the leading edge of the glacier, would have dammed up that river and immediately led to the inundation of all those lowlands and stream valleys, creating glacial lake type. Similar processes resulted in the formation of the modern day Great Lakes. These also were proglacial lakes, and their formation is a lot more complicated. They're deep. I mean, in some cases over 1,000 feet deep, but you can see sort of the relationship over 14,000, 9,000, 7,000 up to more recent times about how those lakes formed right at the edge of glaciation, backing up some of the rivers of the Midwest region. This has happened in a probably even a more dramatic form in Montana. The Clark Fork River was backed up during the Ice Age by the Cordilleran ice sheet, and it had an ice dam that broke. And this was a catastrophic event during the Ice Age. That entire glacial lake drained in a matter of just mere days at best. And all of the washout from that scoured about a quarter of Washington state and completely carved out major gorges and sections of that landscape. That's was called Glacial Lake Missoula. And the landscape that it created in eastern Washington and parts of Oregon is today called the channeled scablands. This happened about 15 to 17,000 years ago. Again, there were people in this part of the world. There were Native Americans here that long ago. Some of them may have been killed in this kind of event, very likely would have. Certainly some of them would probably have been there to observe it. This is what that landscape looks like from an aerial view today. There's various documentaries on National Geographic and elsewhere about this. This is an ancient waterfall. It would have been many times larger than Niagara Falls, as the water would have poured over those cliffs into that basin below. And you can see a lot of the evidence of scouring floods. You know, how much does these types of events through the course of human history, whether it's in, you know, parts of the Middle East or parts of Asia, or parts of here in North America, many different societies have flood origin hypotheses, right? For like the great flood we hear about from the Bible. How many of these actually are passed down through oral histories the native peoples have been telling for, you know, tens of thousands of years? I don't know. It's interesting to think about that there were events like this within, you know, within human societies that could have been passed down as oral stories. Now, a key feature of glaciation that we need to next shift to is sea level drop, right? As we said, there was a lot of the global water was tied up in ice, and so that would have resulted in a major drop in sea level of, what we say, about 121 meters, right? So, for example, the modern day coastline, shown here in dark brown, would have expanded greatly. Under the Ice Age conditions 18,000 years ago, Florida was twice the size that it is today. From somewhere like Mobile or Panama City, Florida, you could have walked out another 100 miles onto the continental shelf. Yucatan Peninsula, Mexico was much larger than it is. Cuba was double the size as it is. So there was a lot more land that could be inhabited or served as migratory corridors, right, for species. Keep in mind what was happening if Florida was getting double the size as it is. What was happening in Tennessee 18,000 years ago? Remember, never glaciated, but what was happening there? It was a lot colder, probably drier. We haven't talked about the climate too much, but the whole ecosystems had shifted. We think instead of being temperate forest or maybe some grassland, it was cold boreal forest, like modern day northern Quebec or northern Ontario. What does that mean for animal migrations? It means that a lot of the species had to shift south. Well, they had extra land to move on because sea levels had dropped. So where is the evidence for this sea level drop and the fact that there were terrestrial landscapes underneath areas that are currently covered by the oceans? Well, just off of Mobile, Alabama, for example, we have buried river channels of the Mobile River and the Pascagoula and the Pearl River to the west. Their incised channels or river valleys are carved into the underground areas of the continental shelf right off the coast. And you can see evidence of that by the dark brown there. We also can look at, for example, recently during some of the hurricanes that blew up into the area of Northwest Florida and coastal Alabama, it had a lot of coastal dune erosion. One of the things that it revealed is when it washed away this beach dune, it revealed the tree trunks of a 60,000-year-old cypress forest. Today, these don't grow in dunes at all. They grow in swampy floodplains. So it indicates there's been a lot of change there. Actually, I'm not sure if these were 60,000. The 60,000-year-old ones are a little bit farther out to sea and about 50 feet underwater. Dendrochronologists, people who study tree rings, have actually dived down, taken cross sections of those 60,000-year-old tree trunks to determine how old they were. So it's pretty cool. There's some publications about that. Chris Gentry, who's the chair of geosciences, one of his good colleagues was involved in that research. So when you see sea level drop, like we saw in the Ice Age, again, this is it 2 million years ago at the beginning of the Ice Age or the end of the Pliocene, when sea levels were kind of high, right? 50,000 years ago, during the Ice Age, we see those levels drop substantially. And this is reflected by the fact that we have where the rivers are flowing down, it creates these river bluffs there. It's part of the clues of the landscape you look at. You can also see that there's a historical coastline that's preserved in the landscape there. That's what this marine terrace and scarp is right there. These are the river bluffs where you had bluffs on either side of a river. But as the waters drop even more, giving us a new coastline right there, then you can see those river bluffs are still preserved. So it's a way to kind of gauge the drop in rivers. They have farther to go to reach the sea. All these landscapes are visible right in here in this region around Mobile Bay. Now, we talked about with all this new land, surely plants and animals must have been taken advantage of. Well, the things that needed warmer temperatures, this is where they retreated to. So deciduous forests came down here. Subtropical forests would have expanded out in here. Maybe grasslands, right? So what's the evidence for all this? Well, it comes from various sources, but I'm just going to hit the highlights. One, we can look at things like mangrove trees. They're found in South Florida. They're found in southern Texas. One of the theories is they must have been able at one time to migrate right along that coastal fringe. Now they can't go that high because the temperatures are too cold, even in South Mississippi or coastal Louisiana. So they probably could have migrated through that corridor at one point in time. We also have fossils of pronghorn antelopes in Florida, and we have modern pronghorn in places like Texas. They very likely would have used that Gulf Coast migratory corridor. And finally, we have burrowing owls. One of the only places east of the Great Plains where you find owls that burrow are in South Florida, in some of the prairies below Orlando. Okay, let's talk real quick for about, we're going to go about 5 more minutes and then we're going to stop. Let's talk about the effect of glacial melt and sea level rise. This map shows the retraction of glaciers during the Ice Age. And so you can see, for example, the areas first to melt are in bright purple, sequentially followed back all the way until we see the areas in white, where there are still glaciers today. Right? So we have some glaciers in parts of Southeast Alaska and parts of northernmost Canada and Greenland. And if you were to put times on these, right, so this would be like 18,000 years ago, then progressively 15,000, maybe 12,000, 11, 10, 9, 8, etc., all the way back until like 1,000 or 2,000 years ago, you can see those glaciers retreating to the north. As this is happening, and you can see this, this is another diagram that looks just at the area over Alaska and Northwest Canada. So here's modern day Alaska. Take a look at the difference. What we're going to do is look at these two colors and the way they shift. So the dark blue shifts to bright blue, okay? So that's older coming to more recent. So dark blue, we had lots of ice, and then it's beginning to retreat, right? It's because the glaciers are melting. And so they're moving into areas where they're lighter blue over the span of just 5,000 years. That's how much they move, from 21,000 to 14,000 years. Look at how much the ice is beginning to shrink. As it does, sea level is rising. It's going to go from brown to green. So these areas shown here at 21,000 years ago, note there is still a land bridge connection through here. But by 14,000 years, that land bridge is completely underwater because of the melting of glaciers. So that window for people to move across via land bridge connections would have been severed. Now, could they have taken a water route? Sure. Or, possibly. That's one of the concepts that's still hotly debated among archaeologists. So there's a strong connection between sea level rise and the retreat. And by the way, this schematic here on the left is just showing that region between Alaska and Russia, which is just separated by a few tens of miles. Okay, what we're going to do is stop here. We're going to pick up on Thursday with the very tail end of the Ice Age, which begins to be a time of extreme climatic instability. We're going to talk about Dansgaard Usker cycles. Okay, that's my best, which are a time of very rapid fluctuations in temperature that are going to help, almost like a domino effect. They're going to help lead to the retreat of glaciation. Again, Milankovitch cycles are tied up in this as well. We're then going to get into some of the hotly debated topics that happened right at the very end of the Ice Age, including what many emerging scientists believe was a massive meteor impact somewhere over Greenland or northern Canada. We're then going to begin talking about the extinction event that happened at the end of the Ice Age that led to the extinction of so many megafauna. Once we get to the end of all that, and I'm going to give you an overview of the kinds of animals and plants that we had here during the Ice Age and the kind of shifts that we would see, then the next natural transition point for us is, let's talk about people. Let's talk about the first people who came to America 21,000+ years ago. And then let's follow their journey through time all the way up until Europeans got here, at which point we'll pick that up. Now, more relevant